Hello everyone, my name is G. Etanavardhan from NIT Andhra Pradesh BTech third year ECE branch. So we're gonna discuss about optimizing nonlinear programming problems with Kuntakar method. So these are the contents we are gonna discuss. First, the introduction to nonlinear programming problem. So first of all, we're gonna see about what is optimization. So, optimization is the process of finding the best solution to the problem from a set of possible solutions which are subject to certain constraints. So, in optimization, there will be two types of problems. One is linear program problem, which will be having only linear constraints and objective function. So, next type is nonlinear programming problem. So, in this, there will be nonlinear functions in the objective function constraints. So, nonlinear program problems can be more difficult to solve than linear program problems because the objective function and constraints may not have simple algebraic form or may have multiple local optima. So, next, this requires the use of more advanced optimization techniques. So, basically, there will be so many methods to solve nonlinear program problems, including gradient based methods, Newton's method, genetic algorithms, convex optimization methods, Karish Kuntakar method, or KKT method. So these are not only the methods, there are several more. So applications of nonlinear program problems. So portfolio optimization. The goal is to find optimal allocation of assets in portfolio that maximizes the return and minimize the risk, subject to various conditions. Second one, chemical process design. It helps to determine the optimal operating conditions that maximize the yield and minimize the cost of production. Machine learning. So basically, in recent years, due to the increase in use of machine learning, so there will be use of optimization with the help of nonlinear programming problems. So that involve nonlinear object functions and nonlinear constraints. It helps to find the optimal parameters for machine learning models. Next one is structural optimization. Nonlinear program problems is used in structural optimization to determine the optimal design of the structure that satisfy various constraints such as stress, deformation, stability. Image processing. So nonlinear programming is used in image processing for image restoration, image segmentation, enhancement, etc. So next, Karush Kuntakar method or KKT method. So KKT method is widely used for solving nonlinear program problems. It will be having some conditions, so it has to satisfy those conditions for solving these nonlinear program problems. These conditions represent necessary for optimal solution of nonlinear program problems with inequality and equality conditions. The KKT conditions involve the gradient of the objective function, the constraints, and the Lagrange multipliers, which are introduced to incorporate and constraints into the optimization problems. So now we are gonna discuss about conditions for KKT method. First condition, dou L by dou x1 is equal to 0. Here L is Lagrangian function. And second conditions, dou L by dou x2 is equal to 0. Next, we can continue these conditions if we are having more than two variables in the objective function. Third, third condition, lambda into h is equal to 0. Here, h is the constraint equation and lambda is Lagrange multiplier. Fourth condition, constraint should be greater than or equal to 0. Fifth conditions, the variables present in the objective function should be greater than equal to 0. Sixth condition, lambda is greater than or equal to 0 for maximization of objective function, or lambda is less than or equal to 0 for minimization of objective function, where lambda is Lagrange multiplier. Next, complementary slackness. The product of each Lagrange multiplier and its corresponding constant must be equal to 0. Dual feasibility. The Lagrange multipliers of the optimal solution must be non-negative. primal feasibility. The values of the decision variable at the optimal solution must satisfy the constraints. Now, solving nonlinear program problem example using KKT method. So, the KKT method can be used in optimization of power in a PAM modulator device. So, here PAM, pulse amplitude modulation, is a modulation technique used in digital communication system to transmit digital signals over a communication channel. Here, the PM modulator device, the power consumption can be critical factor that needs to be optimized. So so basically PM modulator can generate multiple PM signals simultaneously. So there will be multiple signals coming out from the PM modulator. So next, pulse amplitude modulation. So pulse amplitude modulation technique used in communication system to transmit analog signals over a digital channel. So these will be helpful in many applications. So optimizing the power in the PAM modulator will be very useful because we are using PM signals frequently. So the advantages of PM are its simplicity and low cost. So it is widely used in applications such as digital audio, voice communication, and voice transmissions. So in this optimization of PM modulator, one of the method to optimize the power is power of the signals. So the power consumption of the PM modulator device is calculated as a formula: P is equal to A square into T into F divided by 2N. So here, where A is the amplitude of the pulse signal, T is the pulse duration of pulse width, F is the pulse repetition frequency, N is the number of pulses in the signal. If you are taking for NPM signals produced from the PM modulator device, then we can formulate the objective function by taking the power formula and taking amplitudes as variable and remaining T, F, and N as constant. So here objective function will look like P is equal to A1 square x square plus A2 x square plus so on AN x square. In optimization of PM modular device, we want to minimize the power consumption according to the constraints. Here, A1, A2, A so on, AN can take any values as their constants. In the example, signal are used to perform PAM. So for two PM signals, objective function will look like P is equal to 2x1 square plus 3x2 square. Here P is the power and x1, x2 are amplitudes of the signal. Here constraints will be written as x1 plus x2 greater than or equal to 1. So it will be converted to minus x1 minus x2 less than or equal to minus 1 and x1 x2 greater than or equal to 0 as amplitudes are always positive. So here constraints take care of sum of amplitudes not less than 1. In the above, constraint is applicable only if like x1 plus x2 greater than or equal to 1, due to which if amplitude sum leads to less than 1, which gives rise to very negligible values of respect to amplitudes. That is, if sum of amplitudes is between 0 to 1, then the respect to amplitudes will values will be decimal values between 0 to 1. So which is practically hard to replicate. So we'll be taking constraint as x1 plus x2 greater than 1. So this objective function is in nonlinear programming problem as quadratic programming problem. So in KKT method, we are gonna having conditions to solve these type of nonlinear programming problems. So by using KKT method to solve NLPP problem, which contains two variables and one inequality condition. So these will be the conditions for minimization of the objective function. So here that is power. We should have to minimize the power of the PEM modulator. So here main important thing is lambda should be less than or equal to 0 for minimization, where lambda is Lagrange multiplier. So next, we can write the Lagrange function as L of x comma lambda that is equal to objective function minus lambda into the constraint. So that is 2x1 square plus 3x2 square minus lambda into minus x1 minus x2 plus 1, where lambda is Lagrange multiplier. So here the dou L by dou x1, that is equal to 4x1 plus lambda equals 0, and dou L by dou x2 is equal to 6x square plus 6x2 plus lambda equals 0. And from third condition, lambda is equal to lambda into minus x1 minus x2 plus 1 equals 0. And by fourth condition for KKT, lambda less than or equal to 0. And fifth condition, minus x1 minus x2 less than or equal to minus 1. And at last, x1 and x2 greater than or equal to 0. Next, we will be having the following case. So, in the case 1, we are going to take lambda equal to 0. From first and second equation, we have x1 equal to 0 and x2 equal to 0. So, it doesn't satisfy the equation 5, that is minus x1 minus x2 less than or equal to minus 1. So, this case is not considered. In next case, lambda is not equal to 0. From equation 3, we're going to take lambda not equal to 0, then minus x1 minus x2 plus 1 should be equal to 0. So then from equation and equation 2, we can get x1 is equal to minus lambda by 4 and x2 is equal to minus lambda by 6. By solving equation 3, we can get lambda is equal to minus 25 by 10, that is minus 2.4. By this, we're gonna substituting the lambda in this x1 equal to minus lambda by 4 and x2 is equal to minus lambda by 6 equations. We can get x1 equal to 0.6 and x2 is equal to 0.4. So hence the stationary point will be x1, x2 and lambda values will be 0.6, 0.4 and minus 2.4 respectively. So we're gonna substitute these x1, x2 values in the main objective function, that is p is equal to 2 of 0.6 whole square plus 3 into 0.4 whole square, that gives us 1.2. This will be the minimum power of the PAM modulator. So this is the source code. So this is the source code of this problem. First, we're gonna import the minimize function from the SciPy optimize module. From we have to import minimize function. First, we are gonna define the objective function to be minimized. So we're gonna return 2x1 square plus 3x2 square, and we're gonna define the constraint function, that is x1 plus x2 minus. Next, define the KKT condition, that is gradient of the objective function and the constraint function. So this, so the gradient of the, that is first condition, that is 4x, and next one is 6x. To find the minimum of the objective function subject to the constraint, we're gonna use these, and we're gonna extract the x1 and x2 values. So we're gonna print the optimization result and the values for getting optimization, that is optimal values of x1 and x2. We're gonna get this from the source code. We're gonna run this code and see the output. Now we can see that we got the minimum value of the objective function, that is power 1 is equal to 1.2, and optimal values of x1 and x2 are 0.6 and 0.4x respectively. So these are the values which we got earlier by solving using KKT conditions. That is x1 is equal to 0.6, x2 is equal to 0.4 and lambda is equal to minus 2.4. And the minimum power we got is also 1.2. Coming to conclusion, the KKT conditions provide a powerful framework for solving nonlinear program problems with constraints. So we observed that by using KKT conditions, we solved the nonlinear programming problem and got the values, optimal values for the optimization objective function. These conditions involve gradients of objective function, the constraints, and the Lagrange multipliers. The KKT conditions are essential for formulating and solving optimization problems in a wide range of fields, including engineering, economics, finance, and management. The KKT conditions also provide a powerful and necessary tool for solving nonlinear programming problems with constraints. Thank you.